do appreciate everyone coming, and we will start our webinar. Reactors and ProMax. There are a number of reactor shapes that you will see when you go under the ProMax reactors shapes that appear in the list of shapes on the left-hand side of a typical ProMax screen. Most of the time, the typical shapes that I've seen are either this vertical reactor, the horizontal reactor, the burner, there's the sulfur redistribution, the sulfur condenser, and one of these burner/incinerator type stack setups. Those are the most common ones that I've seen used. They're all the same on the inside. They can all do the exact same types of reactions. It's just whatever happens to be the most appropriate shape for what you have in your project. We'll go through how to set these reactors up for the different kinds of reactions that ProMax can model. In these reactors, ProMax can model either Gibbs minimization reactions, it can model equilibrium reactions, conversion reactions, and kinetic reactions. The big difference between Gibbs minimization and these others are these three are what we'll refer to as molecular reactions, meaning that you have defined a specific path, a specific reaction of a set of reactants, a set of species as reactants, and you create a set of species that are products. And you set up the stoichiometry and all of that good stuff so that you have the reactants moving to the products and making it go in that way. The Gibbs minimization approach just looks at all of the species that are present in your environment, or specifically which species you have said you can adjust or change atoms between. And ProMax goes through and says, okay, what happens if I adjust the compositions of these species, and can I find a place where the Gibbs energy of the system is then reduced or minimized? And as it goes through, it will then give you effectively what the equilibrium position is at a given temperature and pressure, but it does not care about reaction pathways. Stoichiometry will still appear because the number of atoms of each element will not be lost and it won't be changed. So the total mass of the system remains constant. The number of moles can change, but the total mass of the system is constant, as well as the total number of atoms of each element will remain constant. There are two new reactor blocks that are not the same as all these others. There is the alkylation and the delayed coking reactor blocks. These two are specialized blocks that deal with just the hydrofluoric acid alkylation process and the delayed coking process that are typically found in refineries. We won't be going into those two in any detail. If you are interested in those, the 211 course on crude distillation is the course I would recommend that you go to talk about how to use those two reactors. They are very specialized. They are not in any way as general as these other reactors are. So to kind of keep a cohesive discussion throughout all of this, we're going to treat this reaction, which is the water gas shift reaction. We're going to do this reaction and we're going to demonstrate how to model this reaction in these 4 different methods of doing a chemical reaction in ProMax. So we're just going to be doing the water gas shift. There are a couple of things that are special about this. First of all, you'll notice that the coefficients are all 1. So it's going to be fairly easy to put the information in. The number of moles, you'll also notice, does not change. So it'll be kind of hard to see what's happening, but if we look closely, we'll be able to see that the CO is converted to CO2, and the water will also be consumed, and that we end up producing CO2 and H2 as we go through this. All right, so let's talk about that first type of reaction that can be modeled in ProMax. That first one is called Gibbs minimization. This only accounts for production or consumption of species. It does not account for specific types of or specific reaction pathways. Anything is free game, and as long and if you want to look at it as you break all the molecules apart, or all the species get broken apart into their constituent atoms, and then you rearrange those atoms to minimize the Gibbs free energy. And as long as you are producing species that you are allowed to, it does not matter how you get there, or even what the activation energy is for such a transition. As long as Gibbs energy is minimized, it is a valid step. That's it's really nice because it's a very simple way to do reactions. It's very powerful. It does not require any kinetic information or information about the specific pathways. The drawback is that it pretty much guarantees reaching equilibrium. And so if you are trying to figure out what the extent of reaction is for a certain sized reactor, or if you're trying to size a reactor to reach equilibrium, then it gets very, very difficult, because none of that time dependent nature is in the model at that point. In ProMax, you can account for non-equilibrium effects through either a bypass or constraints, but these are going to be more in the sense of matching plant data as opposed to actually trying to determine an extent of reaction a priori, or using a given sized reactor. One of the nice things about the Gibbs minimization is it does allow for complete consumption of one or more components. So you can run a reaction, you can mix hydrogen and oxygen and use up all the oxygen and form water. Some of the other reactor types have issues when one of the reactants goes to zero, and it just gets very, very hard to solve. And some of those may fail at times. The Gibbs minimization, as long as you're willing to accept equilibrium, will allow for complete consumption of one of the reactants. Let's talk a little bit about the various inputs. You'll have to assign a reactor type, and I'll show you how that is done. You can assign a Gibbs set, and I'll discuss a little bit about what Gibbs sets are present and what they do for us. In our particular case, we're going to make just these species active. Only these species are going to be active because these are the species that are present in the water gas shift reaction. You also need to set a pressure drop, and then I'll demonstrate what the effects of the bypass and various constraints are as we go through this, so that you can get an idea of what those do and how they work. We're going to take this as our data. So I'm going to move this over here. So there is our starting data. Here we have a blank ProMax project. So the first thing we're going to do, since this is Gibbs minimization, we don't need to define any kind of reaction. So we are simply going to define our environment. So we're going to bring in our active environment. We're going to, we'll use Peng Robinson. You can use SRK or any other property package as you wish. For this particular reaction, Peng Robinson will work fine. And so our components, we've got carbon monoxide, we've got water, we've got CO2 and hydrogen, nitrogen, and methane. You'll notice that we have a fair amount of nitrogen in this sample. This composition has come from a feed to an ammonia plant. And so the presence of nitrogen is not a bad thing here. So that gives us our components. Now start. We'll have our inlet stream. So we're at 670 Fahrenheit. We're at 375 PSIG. And we'll just stick with 100 pound moles per hour for our demonstration purposes. We'll come over here to our composition. And we'll put in our composition. And we will come and find our reactors. So our reactors, any of these reactors will work as a Gibbs minimization reactor. You can put them in as you wish. If you are not doing heat exchange, then I would stay away from the heat exchanger ones. And if you're not doing a multi-phase, I would stay away from those. So in our particular case, we're going to keep it fairly simple. We're just going to go with this vertical reactor. And we pull out our stream here for our exit. Our inputs for the reactor, we had been told that we need to define the type. So we define our type here. And you'll see that there are conversion, equilibrium, Gibbs minimization, plug flow, with and without mass transfer, stirred tank with and without mass transfer. In this particular case, we're going to go Gibbs minimization. The reaction set, you can put in a reaction set if you wish, and then Gibbs minimization will be performed for just those species that are listed as reactants and products in that reaction set. Or you can put in a Gibbs set. General is the default. It basically says that everything that is present in the environment can react. And so you can exchange atoms between all species that are listed in the environment by default. There are a number of other items here. If you have ever used ProMax for sulfur recovery modeling, you'll know that a lot of these that are listed in here are all based off of the sulfur recovery models that ProMax is used to simulate. There's a few in here that are not. There's the burner. These Gibbs sets are here primarily to allow for some double checking of materials. For instance, a burner checks and makes sure that there's oxygen present and that there's water and CO2 present, things like that. The acid gas burner does some checks to make sure that you have the sulfur species, that you have SO2 and things like that in the environment. If they're not there, then you usually get warnings. And it tells you what species need to go back and be added to be able to use that particular Gibbs set. We're going to leave this as general for now, and we'll put in a pressure drop. We'll come back and discuss the bypass fraction, which is down here, and we'll come back and discuss the constraints in a little bit as well. Some of the Gibbs sets will predefine constraints for you. They will show up here. We're going to come here to the Components tab. As I stated earlier, the general Gibbs set allows all the species to be Gibbs reactive, meaning that the atoms can be spread across any and all of the species that are listed. We don't want the methane or the nitrogen to be considered in the minimization. And so the amount of methane is going to remain constant. The number of moles of methane, let me put it that way, the number of moles of methane in the system are going to remain constant. The number of moles of nitrogen are going to remain constant. These others can change. Whether they do or not is all going to be based on what the minimum Gibbs energy is going to dictate. That is all that is needed to create a Gibbs minimization reactor in ProMax. So if we solve this now, we can come in here. Here on our components, we can see that 81% of the CO was converted, meaning 81% was consumed. 16% of the water was consumed, and then the CO2 and the H2 have negative conversion values. The negative conversion values means that they were actually produced in the process that was being modeled. And so this is saying that CO and H2O were reacting and they were producing CO2 and H2. If we look at our streams, you'll notice that adiabatically we have increased in temperature. Ijaz, I will get to that real quickly. The big reason that we left it out is that we are modeling specifically the water gas shift reaction. And so we don't want to have, there's no methane that is going to react here. I'll show you what happens though if we leave the methane in there in this particular case. In this particular case, the adiabatic system increases in temperature. And so we could determine what our heat of reaction would be. We have our pressure drop of 5 pounds. We have the same number of moles, and that's because the reaction that has occurred is simply, or is equal molar on both sides. And so there's simply no change in the number of moles. But if we look at the composition, you will see that the number of moles, or the concentration of CO and for H2, have gone down, while the number of moles, or the concentration of CO2 and H2, have gone up. The N2 and the methane are constant. It was asked, what happens if we leave the methane in? Well, if we leave the methane in, then we can allow the methane to form CO and H2, or CO2 and more H2. And so we could allow for steam methane reformation as well as just the water gas shift. And so if we execute this, actually we're now producing a whole lot of methane. And so we aren't at a high enough temperature to push to run the steam methane reformation reaction in the form of forming hydrogen. Instead, what we have done is we have now reacted the hydrogen with the CO to form methane. And so now when we look at our streams, you'll see we have increased in methane, and the concentrations have changed because it's no longer equal molar. So let's go look at this on a molar flow basis. The number of moles of nitrogen is constant because it's not reacting, and even if it was allowed to react, it couldn't react to anything else. We've produced methane. We have reduced the amount of hydrogen in the system. We have, so some CO2 has been produced, some water has been produced, and a lot of the CO has been consumed. Which species you allow to be Gibbs reactive can change what is going on in your system. And so if you want to be fairly specific on what is allowed or not allowed to react, you will need to make sure that you have correctly set this up. Without that methane being reactive, we get the production of hydrogen rather than the consumption of hydrogen. So this gives us an equilibrium system to address the fact that not all systems reach equilibrium. There are a couple of ways that you can work with a Gibbs minimization reactor to address that and mimic a system that does not reach equilibrium. One of the easiest ways, and it is one of the ways that is used in the sulfur recovery units, is to address the bypass fraction. So the bypass fraction is nothing more than saying how much of the feed does not react. So 5% of the feed is simply going to pass through the system unreacted. And so if we execute this now, you will see that we don't have 81% conversion anymore. We're down to 77%. And if we look at our streams, you will see that we have the reaction still goes, but it does not go to the same amount. And we still have so we end up with extra unreacted material in the end. So the bypass is one way to adjust for not reaching equilibrium. Another way is through the use of constraints. There are a number of different constraints. Many of these constraints are directly related to sulfur recovery. The Fisher, the NSERC, and the Lewinska-Dehern are all related directly with sulfur recovery. The GPSA hydrolysis is also sulfur recovery related, but these others can be used pretty generally. The linear, the quench inlet offset temperature, the quench temperature, and user defined are all very, very general. I'll demonstrate a linear here real quickly. The linear constraint basically defines, given a certain amount of material on the inlet, the linear constraint then says this is the amount that will be coming out. So if I have 1 mole coming in, I can have this constraint determine how much should be coming out. It also allows me to define exactly how much should be coming out. So for instance, I want to say, so CO2, let's take a look and see how much CO2 is coming out. In the equilibrium point, it's saying that we have about 11.5 moles of CO2 coming out. So I could come in here for my CO2 component, set my offset here, and I can make it either more or less than that amount. So I could say that I want it to be 10 pound moles per hour exactly. And so now, when I run this, my outlet is going to be 10 pound moles exactly of CO2. And so if you know what your amounts should be to match plant data, for instance, for a given reactor, you can do that. And then the other items are going to adjust in accordance to meet the minimum Gibbs energy, assuming that that one composition is going to be as you stated. Now, the one thing you need to pay attention to with this is that it can become very tricky because that 10 pound moles is going to remain constant no matter what. So if I come over here and change my inlet flow rate by a factor of 10 and rerun this, I am still going to have exactly 10 pound moles of CO2 coming out, even though the amount at equilibrium would be very different from that. So that's one of the things that you'll have to be careful with the constraints, is that, and especially the linear constraints. If you can set up a change aspect, this is effectively the slope, and this is the intercept for a linear line. Right now, we're saying there is no slope, and that slope would be something that would allow things to change based off of how much CO2 is coming in. There are ways of working with that, and so you can use this to model a range of data and come up with a very nice model that will represent your particular plant, but it will be for the data that you have used in your correlation. So effectively, you're coming up with a numeric correlation to match your data in this case. There are lots of neat things that can be done with Gibbs minimization, but it does have its limitations. As you can see, you would have to have this correlation, or at least data to make the correlation. It's not something that the system would be able to come up with on its own. So the next type of reactor, and this is going to be the first of what I called what we have classified as the molecular reactions. All these other reactions are going to require us to put in a reaction pathway into ProMax, so that ProMax knows what is going to react and what is going to be a reactant, what is going to be a product. One of the easiest reactions to model are the equilibrium, is an equilibrium reaction. This effectively is going to give you the exact same answers as the Gibbs minimization. Well, I guess the difference between this and a Gibbs minimization would be how close our energies are compared to the lab data that you have collected or are using to determine your equilibrium constant. There are some benefits to this. It limits you to a specific reaction pathway. You don't have to worry about other things getting in the way and having some odd side reactions occurring that you really don't want to have occurring. The equilibrium constant either comes from the Gibbs free energy, or it comes into a polynomial expression. This is the polynomial expression that ProMax has built into it. You have a constant term, you have a 1/T term, you have a log of temperature term, and then you have a linear and quadratic term, all of which are related to what the ln of what the log of the equilibrium constant is. You can still do a bypass on these reactors, so that would work just fine. There's also, it will also allow you to have a temperature difference between the system temperature, meaning the temperature that the stream is at, and the temperature at which the equilibrium is calculated at. This can become useful if you have a heterogeneous catalyst and the catalyst temperature operates at a different temperature than the bulk or the stream temperature. So for instance, the catalyst temperature might be warmer than the system temperature because it's an exothermic reaction that's occurring on the catalyst. Or it might be an endothermic reaction that's occurring on the catalyst, in which case the catalyst is at a lower temperature than the system temperature. And this will allow you to better mimic what you're seeing in your plant with regards to the equilibrium reactors. So here, the things that we'll need to do in ProMax is the first thing we need to do is we need to create a reaction set, and I'll go through and show you how to do that. We then get our reactor type, and then we will assign the reaction set to our reactor block so that we can then run the reaction, and we have to set a pressure drop. And so these are the items that have to be put into ProMax. We're going to use this information for our gas shift reaction. In this particular equation, our temperature units are in degrees Rankine, and that's going to give us our calculated equilibrium constant. I'm going to add a new flow sheet, and I'm going to use a copy of the environment so I don't have to put my components in. This is going to be my equilibrium reaction. To put in the reaction itself and all of the necessary information for that, we're going to come here to our project viewer. We're going to come over here on the left to this area that says reaction sets. And we're going to double click on all reactions. We're going to create a new reaction. And here we get to put in our information. So we have CO and H2O, CO2, H2. Okay, so I need to provide the stoichiometry. In the stoichiometry, reactants are given negative coefficients and products are given positive coefficients. You'll notice once I have that properly defined that I get a reaction equation up here. If it's not balanced, it will be in a red background. Once it's balanced, it shows up in a gray background. This is saying that carbon monoxide plus water gives CO2 and hydrogen. This is going to be an equilibrium, so I need to provide the equilibrium coefficients as well. So this is what the powers of these components are in the equilibrium expression. So if you go back to chemistry, you have products over reactants. And so you would have something like the concentration of CO2 times the concentration of H2 divided by the concentration of CO times the concentration of water. So these two would be in the denominator, these two would be in the numerator. We need to define the equations to use. In this case, it is equilibrium only. Our concentration, these concentrations are given in mole fraction. You would need to know that. I should have included it on the slide, but that is, you would need to know that going in. So the concentration units, they're going to be fractional. We're going to allow this to occur in the total phase, but we could be very specific and say that this is only going to occur in a liquid phase or in the vapor phase. Total implies that it can occur in any phase that is present in the reactor. In our case, there's only one phase, so it doesn't matter, but if there are multiple phases, you can define which phase it goes into. We're going to skip the kinetic base information because this is not important for equilibrium. We're going to come down here. And so if you select the KEQ from Gibbs, this is basically telling ProMax to determine the KEQ from what ProMax calculates as the Gibbs free energy. This, in essence, will give you the exact same effect as a Gibbs minimization reactor. We have an expression, though, where A is minus 4.33 and B is 8240. C, D, and E are zeros since they are not present in our system. This approach temperature is how you can allow the temperature of the reaction or the equilibrium constant to be a different temperature of the be used in calculating the equilibrium constant rather than the stream or the system temperature. An approach temperature of 0 means that you are using the system temperature. We'll go ahead and use that for now. We'll come back and we'll show you what the effect of that, of changing that is in a little bit. And so we can click OK here, and that has created a reaction. I should have changed the name. So this is equilibrium water gas shift. So this all reactions set is all the reactions in our project. What we really want is a subset of all the reactions in our project. So to create a subset, we right click on reaction sets and select add. And then we can add the subset of reactions that we want in this particular set. Right now, there's only the one. We'll click OK. This is for what type of reactor. It's going to be equilibrium, and it'll be equilibrium only. So we're going to deselect the kinetic. We're going to make this reaction active. And we're going to rename my reaction set to equilibrium. So that has created our reaction set, our reaction and our reaction set. We will close this. We now need to add our reaction set to our environment. So I'm going to go to our active environment. I had made this a copy of the original one. And so my components are still here, but I need to come here to the reaction sets tab and select which reaction set I want to pass into or use in this environment. You can have multiple reaction sets listed. You can have multiple reactions in each reaction set. Right now, there's only one reaction in this reaction set, but you could have multiple reactions. All right, so now let's rebuild our system a little bit. I'm going to cheat and I'm going to copy and paste my inlet stream. I'm going to come over here to my reactors and bring in a reactor. All right, so this time our type is not going to be Gibbs minimization, it's going to be equilibrium. What reaction set do we want to use? We're going to use the EQM reaction set. If you come here to the reactions tab now, it will list what reactions are available. Okay. And if you come to the reaction set tab for the reactor itself, you can actually come in and change various aspects of all of that data that we set originally. And so you can come in and tweak each of these reactions within the reaction set for this specific reactor. Changes made here are only for the reactor, and they are not reflected in the reaction that's listed over here in the reaction set, and they are not reflected in any other reactor that uses this reaction set. It would be applied just to this reactor. Let's finish our specifications. We need a pressure drop. And that has set up our equilibrium reactor. And so all that we could now execute, we should find that we have roughly the same amount of reaction occurring as our Gibbs minimization. It's not quite exactly the same, but this is using that expression for the equilibrium constant and not Gibbs free energy directly. This will give you an extent of reaction. We have reacted 64 pound moles per hour. So 64 pound moles of CO, 64 pound moles of H2 have produced 64 pound moles of CO2 and H2. I believe that's because I still have my 1000. So we'll go back to 100. We can come back here, set this to 100. And just to show you that everything is more or less the same, we won't run with constraints. And so here we get 81.1% conversion of CO. Here, we are getting basically 81% conversion of RCO. So they're very, very close. Here you can still use the bypass if you wish to modify how much of the process reaches equilibrium. You'll notice that our outlet temperature is very, very similar to the Gibbs minimization case. We can come in and demonstrate what this approach temperature does. So the approach temperature, let's pull up the help and I will action sets. So the approach temperature for equilibrium, it's the difference between the actual temperature and the temperature used to evaluate the equilibrium constant. So if we have a positive value, that means that the reactor temperature is higher than the temperature used to evaluate the equilibrium constant. If this is an exothermic reaction, that means that you are actually going to have higher conversion than what you would expect, because you're saying that the equilibrium is going to be modeled at a lower temperature than what you actually are seeing. So if I set my approach temperature here to 10 degrees, I should get a higher conversion than what I had before. So if we come in here, we now see, you can see that I've now got closer to 82% conversion. And that's because the equilibrium constant is being calculated at 10 degrees below the system pressure, which is at 798. If I make this a negative value, that means that the equilibrium temperature is going to be higher than the system temperature. And for our exothermic reaction case, that means I will have less conversion than what I had at a zero temperature approach. So if we come back here, well, that's at 80.2. And I am at 796. So this is a lower temperature than what I had, but that's effectively what we end up with. We have less reaction, and therefore the final temperature is different. 797.5 and 80.9. We're at 80.2, so we have lower conversion, and we are slightly cooler coming out because we have less reaction occurring. That's one of the other ways that you can work to match plant data when using an equilibrium reactor. So you can use your data to form the necessary coefficients for this expression here. Or you can adjust this approach temperature to better match your plant data. So that gives us an equilibrium reactor. Our next reactor is going to be a conversion reactor. Conversion reactor is very, very basic. It's going to say how much of the, or what is the fraction of the component you're interested in, what of the component you're interested in, what fraction of it is converted. It is a forward-only looking system. You can only look at how much of a reactant is converted. And so it's basically just going to look at a forward reaction only. All right, then, let's talk a little bit about the conversion reactors. It follows a very simple quadratic expression in temperature. And so you can set an exact amount of conversion. If you want to say 100% is converted, you can set that A factor to 1 and leave the B and C to 0. And all of that component will then be converted. If you want to always have 75% conversion, then it's that A value is 0.75. And so you would have your fraction conversion calculated from this expression. You can have multiple conversion reactions listed, and you can adjust them in priority and a number of different things so that you can quickly and easily model a series of reactions that you know are going to reach a certain amount of conversion. This is a very simple, straightforward process. You create your reaction set again, you assign your reactor type, and you get your reaction set in the block, and then you set a pressure drop. Let me quickly go through this, and I'll show you how to do the conversion. So let's add another flow sheet. We're going to duplicate this one again. And this is my conversion. So we're going to take our stream 1 again, paste it in here. Oops. We need to create our conversion reaction set. So again, we come to our all reactions. We're going to create a new one. And so our components are exactly the same. So we need to set up our stoichiometry again. And so it's negatives for reactants and positive for products. This is going to be forward only. Mole fraction and fractional, which is the default. We're going to come down here. We have to define a conversion base. The conversion base is what of the species is this based off, is this conversion based off of? So we're going to go with CO. What units do you want to have for your temperature? I'm not going to worry about the temperature terms for now. So I'm going to leave that as K, but you can change that temperature between Kelvin and Rankine. And we can now come in and set a conversion basis. So we'll say that 75% gets converted of our CO. We'll click OK. We're going to create our reaction set. Again, you right click on reaction sets and click add. This is the conversion. So this is a conversion reactor. So we'll pull everything else off, and we're going to add, oops, I didn't change the name. So I want to come over here. This is my conversion water gas shift. And then here, you add the conversion water gas shift. You'll notice I could select and I could add the other one in as well if you wish. So you could have multiple reactions in a reaction set, and then you could select what you wanted to have modeled. In this particular case, I don't want this one in here, so we're going to remove it. Now I deleted it, but it only deleted from this reaction set. If you come over here to all reactions, that equilibrium one is still present because it's in the other reaction set. All right, so that's given me that reaction set. I want to come to my environment, and I need to add my reaction set in. I only want this one for now because that's the only one I'm working with, but I could have both of them present in my environment. And then I could have an equilibrium reactor and a conversion reactor sitting on the same flow sheet. All right, let's build our reactor. So this type is conversion. We'll use our conversion reaction set. And we can execute. So all we needed, so those were the only inputs that we had was the type, the reaction set we wanted to use, and the pressure drop. We get 75% conversion of my CO. And so this is a very straightforward, very simple process to allow the system to model a reaction to a given amount of conversion. If you have multiple reactions and they're all related to the same component as the base, it will model that. You can also model situations. For instance, if we come in here and we want to change our conversion base to water, and we want to react all the water, if we execute that, you'll notice that there is a warning that occurs down here that says that it is unable to achieve, and unfortunately I can't make it any bigger, but it says that it is unable to achieve the conversion of 1. It can only achieve a conversion of 0.20 or 20%. The reason for that is that once it has converted 20% of the water, it has consumed all of the other reactant. And so you can't reach 100% conversion of water because there's not enough CO in this particular case to react all the water. And so you can set things up, and if there are issues with the amount of conversion that you are trying to reach compared to what is possible, it's not going to fail anything. It will give you warnings, though, that will pop up. And so you can see that it's still converged. We still have a reaction that occurred. All of our CO got converted, and we have a fair amount of water that's still left. But that's what the conversion reaction does for you. As far as reactors, as molecular reactors are concerned, the conversion is probably the easiest one to work with. It's probably also the one I use least because most of the time it's just going to model a specific amount of conversion, and that's usually what you're trying to figure out. You don't know that number, and so you're trying to calculate that number. All right, let's move on then. We'll come here to the kinetic reactors. If you were with me a couple weeks ago when I was talking about the reactive distillation, some of this is going to be a repeat of that, but it's for kinetic reactors. ProMax uses a generalized Langmuir-Hinshelwood type of expression for the rate. You have a forward rate constant. You have the order of the reaction with regard to your forward reactant component, and that gets multiplied through all of the forward reaction components. You have a reverse reaction, and so you have the reverse reaction rate constant, the components involved in that reverse rate, and their orders. You can also have an absorption term or terms, depending on whether this is going to be on a heterogeneous catalyst and whether those absorption terms come into play or not. And so you have the absorption coefficient, you have the component or components involved in that absorption and their orders. You have a constant out front, and all of this gets raised to a specific order as well. Most of the time, this order is 1. This constant is 1, and that's the default settings for those. But when we go into the interface, you'll see that you can change those for the cases when it is different. This setup can model just a straightforward reaction. It can model a forward and reverse reaction. It can model a forward plus equilibrium. So rather than having an actual reverse rate constant, you have a forward rate constant and an equilibrium constant. You can do reverse plus equilibrium. So you have an equilibrium constant and the reverse reaction rate constant. You can have any and all of these with or without the absorption terms. So this K value can be 0 effectively if you don't have any absorption terms. So it's a very generalized expression. Depending on what type of reaction you have or what information you have in your reaction rate will depend or will determine what data you have to put in. The forward and reverse reaction rates are given an Arrhenius type of reaction rate. So you have a pre-exponential. There is the opportunity to have a direct temperature dependence. And then you also have the exponent temperature dependence with regard, and it comes into the activation energy. The activation energy here is, this negative sign is assumed to be there. So if you have, so this expression here, if it's supposed to remain negative, you will leave it, you'll put in a positive value for the EA or your activation energy. If the exponent turns positive, then you'll have to put in a negative value for the activation energy. That negative is assumed to remain, it is assumed in the expression that ProMax uses. The absorption constants follow a very similar type of expression with regards to temperature. This is a pre-exponential, and this is the activation energy for absorption, not for the reaction. So let's add another flow sheet. We're going to create a new environment. Again, you don't have to. I've just been doing it so that I can keep everything separate. And when I send this out, everyone will be able to see the different versions without getting everything all mixed up, or at least too badly mixed up. So this is going to be kinetic water. We will copy our inlet stream again. We bring in our reactor. So we have our drawing done. We now need to go create our reaction set. And so we're going to come over here to all reactions, and we're going to first create our reaction, and then we'll add it into our reaction set. So we're going to create a new reaction. This is our kinetic water gas shift. Our components, we got CO and water going to CO2 and H2. Now, we don't need to provide the equilibrium, but we do need to provide our forward and reverse orders of reaction. So CO and H2O have orders of 1, and the other two are 0. The reverse, our reactants have orders of 0, and the reverse is 1. And so that is the way that we need to set up our forward and reverse reactions. Okay, we need to set, so our orders are based off of what our rate expression is. This is actually going to be a forward plus equilibrium because we have an equilibrium constant. We don't have a reverse rate constant. So we're going to change this to forward plus equilibrium. The concentration types are mole fraction. So we need to set this to mole fraction. We're going to set this to total. The kinetic base. So this is what is the component that was used in measuring the reaction rate in the data. And this is coming from CO. I don't believe I put the reference down for where this is all coming from, but I do have a reference for it. So we now need to include our information here. Our temperature is in Rankine. K naught is 1274.44. So you can put it in as the actual value or as the logarithm of that value. You can put in the EA or the EA over R. In R terms, the EA over R is negative 8820 over T. And so the 8820 is the EA. This negative term is implicit, and so we actually are just going to put this in as 8820. We need to provide our equilibrium constant. Again, this is in Rankine, and we're using the exact same equilibrium constant that we had before. There are no adsorption terms, but if there were, you would come over here and you could input your K naught, the EA for the absorption, the orders of the absorption of the components for that absorption term. And once you make one of these active, you would then be able to define the overall order. This is the K exponent, or the constant. And this is the A in the expression in this expression here. So the order is this K, and the constant is this A. All right, so the rate expression is the units of the rate expression are given in moles per mass catalyst. And so our units are pound moles per pound hour. And so I need to change this second into hours. And the catalyst particle density is 126 pounds per cubic foot. And that sets up our reaction. So we have input, our forward reaction rate in Arrhenius form. And we have put in our equilibrium constant so that we have our forward plus equilibrium. We have our units correct, and so everything should be good. Now I'm going to come in and add. And this is kinetic. Oops. Kinetic. And this is going to go into kinetic reactor types. And we're going to make this active. So kinetic reactor types in ProMax, if you look here in the list, there wasn't anything here that listed as kinetic. But plug flow or stirred tank or the plug flow or either of those with mass transfer, those are the items that you would have to work or that you have to work with for a kinetic reactor in ProMax. I'm going to go with plug flow. Since all of this is a single phase, then there's no mass transfer aspect of what's going on. So we're just going to stick with plug flow. I need to add my reaction set to the environment. So we're going to open up my environment and we'll come here to reaction sets. We'll add the kinetic reaction set. And now I can add this in. We'll go with our 5-pound pressure drop. Now, because this is done using reaction kinetics, the amount of conversion is going to be dependent on the residence time. So the residence time has to be determined. To determine the residence time, we have to input information about the size of the reactor. So in this particular case, we have a 19-foot long tube that is 12 feet in diameter. It is 32 gauge. I have one tube, and it is a single pass tube. Okay. So this defines the size of the reactor. We have a 12-foot effectively tube that's 19 feet long. We have one of those. There's only one pass of the fluid of our fluid through this. We do need to adjust the void fraction. The catalyst void fraction is 44.4%. So the reaction is only going to occur on the roughly 56% of the volume that is not void space. The thickness is required because we're using the inside diameter to calculate the actual volume of the system. The outside, so the 32 gauge is there to determine how thick things are since we set an outside diameter. So the question was, why is the BWG required? And that is why it's required, is so that we can determine what this flow area is. That flow area is going to be based off of the inside diameter. So that has now defined the size of our system, and effectively here is the volume. We multiply those two together to get our volume of the system, and then we'll multiply it by our void fraction. or I'm sorry, 1 minus the void fraction to determine what is the reaction volume that we will be working with. And so from here, we should be able to execute. And now, again, you can see that we're pretty much reaching equilibrium here. But if we were to come in here and reduce this and say it's only 5 feet long and execute, being very, very finicky. But we could also come in and reduce our temperature a little bit. What happens if we drop our temperature? And now we get even more conversion. Part of that is because it's an exothermic reaction. The cooler system allows it to reach a higher, if we reduced our system here. Granted, my flow rate was really, really small. So these numbers might be part of, or that might be part of the reason my overall flow rate through the system would have been very, very slow. So there we go. Now we're starting to see some effect of the system size. It just goes to show that if your system is big enough, you do reach equilibrium. You can now come in and see what happens. And so there we only get 10% conversion. So a really small system. So as you change your system size, you will get to see different amounts of conversion. Those different amounts of conversion will result in different outlet temperatures as well as compositions. That pretty much covers all of the different kinetic reactors that we have in ProMax. Hopefully this was useful for you and has given you an idea of what can be done in ProMax. The reactions are very, very useful and general. You can do a lot of different things with them. It's just a matter of what data you have and how much you're willing how much information you're willing to either guess or put into your model. Thank you all very much for your time. I do appreciate it. And I hope it was worth the time you put in. We will look forward to seeing you in the future.